Okay. Continue. Let me see if the outline works. Okay. Yeah. Okay. Good. So what I will be, sharing with you the upcoming 1 hour. So kind of a tutorial-based presentation or talk regarding in-memory computing. Let me go to the next slide. So starting first, I will highlight first actually the opportunity, especially these IoT and edge devices are booming, are growing, and we'll take a look at what are the major challenges we are facing there. Okay, specifically from a hardware point of view. Then I will move ahead and try to classify the all existing computer architectures. I'm sure you heard in the community, about many topics ranging from, or many names ranging from in-memory computing, logic in-memory, computation memory, near-memory computing. All this, there is so much terminology. I will try to classify the computer architecture, at least try to unify the terminology, at least for this presentation, to ensure that we are talking the same language. After that, I will focus on computation in memory, right? What is it? What is the principle working? Are there any step processes within it? What's the circuit design? Is there interference? How we can perform logic operations? How we can perform arithmetic operation, vector multiplication, and so on. And then show you, first based on simulation and thereafter based on silicon result, what is really this potential of computation memory? Is it really, is it going to bring us something breakthrough, order of magnitude improvements as compared with the state of the art? And finally, I will highlight some challenges from different perspectives, from technology, architecture, mapping, microarchitecture, reliability, testing. There are so many open questions which are actually, from research point of view, very important to explore. And finally, I'll conclude my talk. Feel free to stop me and ask a question, no problem. Let's make it informal. I will be happy to take any question if there is any. Okay, so what's actually the opportunity, right? So on the left side of my slide, you can see the expected growth of IoT devices, Internet of Things devices, reaching almost 80 billions in 2025. That's very remarkable. This is, if we take into consideration, or if we combine this IoT growth with edge computing, the right side of my slide, then we can say that this provides a unique business opportunity. Edge computing means actually doing computing and extracting the information locally where the data is generated, not necessarily sending the data all the way down to the cloud. Think, for instance, about deploying intelligence in the edge for instance, personalized healthcare, wearable devices, or robotics, and so on. So, but this kind of computing and this kind of applications, they have some severe requirements, ranging from energy constraint. A wearable device has it works on a battery, right? So the energy is limited anyways, right? But also, because of that constraint, you need to do local computing. And obviously, we would like to ensure that we deploy some intelligence also at the edge. For example, a wearable device giving the right signal or warning to a hospital, telling that somebody is starting having a serious problem and within 2 or 3 hours will collapse, for instance, just to give you an example. So this should be also real time, 24 hours. And of course, if we are able to succeed to the local computing, then by default, we are solving some data privacy and security issues as well, because data will be then stored locally. You don't communicate data, but instead you communicate the message, the key message you extract from data. So let's now focus on 2 things, the intelligence and the energy constraint, and see what are actually the major challenges there. So this picture is it's known for this ImagineIt project challenge, which is a large visual database actually designed for the use in visual object recognition. So it's kind of a software research. So what you see that, let me maybe put, okay. So you see actually here the top 5 error. So this is actually the percentage of the time that the classifier, so each bar here is a classifier, a version of a classifier, that the classifier did not include the correct class among its 5 guesses. So you have a program, you will make a guess, and in the 5 first guesses, you should guess the right classification to do, assign the object to the right class. Okay, so top 5. So you see that over the years, the accuracy, the error was going down, which means the accuracy is improving, right? Very interesting. So at this stage, since 2015, and then it was because of ResNet. So the accuracy, even though surpassed the human accuracy, the human error. You see this red line gives you the human accuracy. So machines are becoming smarter than a human being. But the key question, that's very nice, okay? Now, the question is, what is the price? To give you an example, this GoGNet had needed 4 GPUs and a training of 2 to 3 weeks. Well, if now we take a look at see how much effort I need of training, so how much resources, effort I need to get to this accuracy, obviously you can see the higher the accuracy, that's good, but the higher the price. An extreme case is the AlphaGo. So AlphaGo is a computer program that plays the board game called Go. And in 2017, this famous player who was #1 in this kind of games, JK, so he played against AlphaGo, against the machine, right? And guess what? He lost a couple of times though. Now, again, the machine is even though smarter than the ranked #1 among all human players worldwide in this game. The guy lost. So, but the question, okay, fine. How much resources was behind this? Well, you can see there. AlphaGo had 176 GPUs and 1,200 CPUs. And the machine consumed 150,000 watts. Well, clearly, if we're going to deploy the intelligence at the edge, like I showed in the previous slide, yeah, these kind of resources are just too much. We cannot do. So if we're going to deploy really intelligence at the edge, we really need something radically new when it comes to the required resources. Now let's go to hardware, see what are this energy, where is this energy actually going? So today's architecture mainly driven by multi-cores, GPUs and multi-cores and so on. They suffer from major challenges, both from architecture point of view, but also from technology point of view. Let's take a look at architecture. So as you know, today machines are mainly phenomenal architectures. Let's take a look at that at this table. So typically, when you order an execution of an instruction, let's say an adding 2 numbers, fundamentally you are interested in doing computing. That's what you want. Okay. So for these numbers taken from this paper, we're talking about 32-bit operand technology, TSMC 14 nanometer technology. Your add operation, which is an ALI, so your ALI will consume about 0.1 picojoule. Let's call it 1x energy. Moving data on chip to or reading from on-chip memory, cache, will cost you 50x more energy. Well, if you have misses and you end in accessing your DRAM, it will cost you 6,400 times more energy as compared with effectively what you want to do. So typically when I'm explaining this to my students in a class, I'm telling them this is, think about, I'm going to give you 6,400 euros to do shopping, and you will spend the whole amount of money to buy a business class ticket from Amsterdam to New York or to San Francisco. You get in San Francisco, you're going to spend €1 on your shopping means typically buying a piece of bread and coming back. It's just clearly very illogical. Does not make any sense. So we need really to do something about it. Okay. So this is what we call the memory wall. But as you know, there are other major challenges our architectures are facing. Amdahl's law is another example, which is ended actually already 2015-16. So meaning bringing too many multi-cores together, 10x cores more, does not mean that you are speeding up the throughput by 10x. Partially because it's extremely difficult to program your multi-core, but partially because of the nature of the applications. Applications, they have also some serial parts that you cannot parallelize anyway. Of course, we have also the power wall. We know that the power budgets are limited. We know that Delft scaling ended around 2010, doubling the functionality at the same energy budget through constant field scaling is not applicable anymore. Power density being constant is not applicable anymore because we cannot scale the voltage as we used to do in the past. So all of this tells you one thing: if you really want to do something about it, you really need to do improvement in the energy, you have to think about a new architecture. So let's take a look at the energy. So energy, as you know, we have to do with two kinds of power: dynamic power and static power. You see the red line gives you the dynamic power, and the black line gives you the leakage power. You see that after the introduction of FinFET, the leakage went down, but still relatively, it's important component as compared with dynamic power. And obviously, ideally, you would like to have your static power equal to 0. To do that, actually, you better use non-volatile technologies than volatile technologies. Not to mention, of course, other major concerns, right? For instance, the reliability. We know that these devices, CMOS devices, the smaller they become, the less reliable they become. Less reliable means that the failure rate, in-field failure rate will go up, and also the lifetime of the chips is reducing. So putting mechanisms to enable reliable circuit is costly. For instance, companies are using adding design gaps, right? Design margins. And when you add the design margins to deal, for instance, with variability, actually you are going against the scaling. So you are reducing the benefit of scaling. So this makes it all difficult. Not to mention, of course, the cost. Making devices below 10 nanometer technology is extremely expensive. I heard from one of these the guys in China in a keynote that this is the guy who is responsible for the head of the microelectronics department in Tsinghua University, that to at 14 nanometer technology node, you need 100 million to 150 million for a new design. And you need to sell at least 30 million chips just to break even. So cost is becoming also a major problem. And this is why you see that all these cutting-edge technologies are mainly deployed in large volume applications like smartphones and mobile stuff. Okay. So again, this means makes sense to explore new technologies, right? Which could be cheaper, which could scale without any problem, which could be, of course, CMOS compatible and so on, and which could enable leakage reduction. Combining this actually means one thing: means we need to explore new unconventional architectures, and by making use of unconventional technologies beyond CMOS technologies. Well, this is actually too risky and against even though the philosophy of commercial companies so far. I think all of you are aware about this TikTok that Intel was adopting since 2007, when actually one time they keep the architecture the same and they scale technology nodes. And once the manufacturing line becomes more mature, they produce the chip. Next time, they will scale down, they will keep the technology the same and modify the architecture. So they prefer to do two changes at the same time because the risk is just too high. And here what we are saying, if we want to succeed, if we want to have breakthrough, we need to take high risks. Okay. So after highlighting the major challenges, let's now move actually to a classification of computer architectures. So actually, we can classify the different existing computer architectures in two different classes. To do that, we're going to use actually this figure consisting of a computing core and a memory core. So depending actually on where the computing takes place or the result is produced, we can distinguish between computation out memory, and we are talking about the memory here, the DRAM, or computing in memory. So two classes. Either you do the computing within the memory or outside the memory. So if we go to computation out of memory, we can actually define two subclasses. One is called far com, which means we are doing the computation far from the memory core. And actually, all CPUs and multi-cores are making use of this far or com far. They are making external of the chip DRAMs, right? And again, as I already mentioned in the previous slide, a reading from accessing DRAM costs you 1,000x more energy than what you're going to spend on the computing. So this communication is actually what kills you. So that's the first subclass of COM. The second subclass is what we call near memory computing. So in this case, the computation takes place not in the memory core. No, it takes place in another block. Think about 3D stacked DRAMs. When you have, let's say, 3D DRAM stacked on a logic layer, like this logic layer. And all of these are in a single chip, what you call system in package. So examples of this kind of designs are hybrid memory cards and high bandwidth memory. So as you know, high bandwidth memory have a huge bandwidth. We are talking about 1024 bandwidth, for instance, and kind of between 200 to 400 gigabit per second. So these are intended mainly to reduce, to increase the bandwidth between the computing core and reducing the communication, making the communication shorter. Making the communication shorter means we are making also the energy spending less. So these are the two different subclasses of COM. We go now to SIM, computation in memory. And also here, we can define two subclasses. So if you go inside the memory, you have actually two main blocks, the memory array, where the storage is taking place, and the periphery around. So if the computation result is produced in the periphery, then we are calling it SIM-P, SIM periphery. And if we are producing the result in the array, we are doing the computing the array, then we are calling it SIM-A. So this is the different classes. So it's very important to see that for SIM, either P or A, we need really modification of the memory core. We need to change something in the memory, in the DRAM itself, for instance, if it's a DRAM or DRAM, whatever. So we need to change the way the design is made for the memory. And this is not necessarily needed for COM architectures. And this is a major difference. Of course, we can also have hybrid architectures, and it's obvious, as you know, that we have COM are commercialized products as of today, but SIM are still in the phase of research and prototyping. Actually, still doing this comparison between SIM-A, SIM-P, and COM-N and COM-F, we can define different actually metrics to compare. I can pick up a couple of them, for example, off-chip data movement, right? So for SIM-A and SIM-P, you don't need to move the data. So data movement, there is no need for it because the data is inside and the computing will take place inside. However, for COM-N and COM-F, you need to move the data. Of course, COM-F, the movement is, because it's far computing, you will spend more energy. Of course, regarding data alignment, if you're going to do computation memory, you need the data alignment. If I'm doing, let's say, ending. Later on, I will show that if you are doing a bitwise operation within the memory, you need to ensure your compiler should map this information in such a way that the data you're going to use will be aligned. Otherwise, it will be just difficult. This is not required, for instance, for computation of memory. The same thing, the bandwidth, of course, the more you are in the memory, the larger the bandwidth, and the COM-FAR is the one with the smallest bandwidth. The same thing, the memory effort you need for the design. Actually, when you are doing the SIM-A or SIM-P, you need a huge effort in designing your memory, okay? Again, you need a significant changes, okay? And of course, scalability. Obviously, multi-core platforms are very scalable. Memory computing, we think it's medium, but also SIM-P. I will come back to this later on. I think SIM-P it's relatively scalable as compared with SIM-E, and therefore, my view, I think SIM-P will succeed much better than SIM-A. I will show that later with a couple of examples. We can also think about other attributes to this classification. Endurance requirements. So, for example, if you are talking about SIM-A, you are accessing the memory frequently, right? So you need to have high requirements for endurance, which is not necessarily the case, for instance, for COM-F. Other metrics for classification, we can consider different technologies, memory technologies. We are talking about computation in memory or out of memory. And the memory could be an SRAM and DRAM and EMRAM and ReRAM and PCM, everything, right? And in your emerging memories. Another component we can use to classify all this architecture is even the computation parallelism task. Computation parallelism. Because usually what we would like to speed up the computation. So in multi-core platform, we are trying to speed up the task. And a task, typically, if you are doing multi-core, typically you have different control units. You are executing simultaneously different instruction memories. You are accessing different data memories. And you have, of course, your multi-core platform should provide you with different execution units. We can say also, instead of doing task parallelism, we can do data parallelism, like is the case for vector processors. And in that case, you are just executing one instruction. So you have only one control unit, but you are accessing multiple data. We can also try to parallelize the instruction, like it's the case for VLIW machines. So taking all of this, actually, we created a nice 3D diagram. So here you see the tasks, here you see the different architectures, here you see the technologies, and here you see what is explored and what is not explored. You see, so the empty spots means the architectures which are not explored yet. So in the rest of this talk, I will be mainly talking about ReRAM or MRAM or PCM. So let's say this is Memristor-based technology. And for SIM-P, mainly, I will also talk a little bit about SIM-A. And in that case, we are mainly talking about data parallelism, just to ensure that we can position this presentation. Okay, so let's now try to understand this computation in memory, the basics. Okay. So this is again your memory core, right? So when we do computation in memory, typically what we are doing, we are sending digital input, right, to our memory core. We are sending an instruction. So what we would like to do is that to get this instruction executed on this data within the memory, right? And of course, we need to get a digital output. And as I already mentioned, these are the main blocks of the memory. You have some periphery, right? And the array. Typically, each block of this can perform a function. So you can perform a function within the array, even though the route decoder can perform a function. Actually, at the moment with IMEC, we are developing kind of a SIM architecture, what you call it, SIM-P architecture, SIM-P basic. So only some changes, a function is included here. I think within a couple of months, we'll have a publication about that. So showing actually that SIM can be created without not changing the array at all, just by integrating some functionality in the route decoder. In a similar way, you can integrate the function in the array, but also in this periphery and so on. And you can also have a complex function performed in the same device through combining this R function and F function and P function. So, of course, depending on the function you're going to implement, the execution you want to do, you may or may not need digital analog converter. If you are, for instance, doing bitwise operation digitally within the array, then you don't need to convert your digital to analog component. However, if you are doing, for instance, neuromorphic computing, and you need to do analog vector matrix multiplication, so you need to compile or to map your digital input to an analog value that should feed your memory array. And of course, your output here will be a current, an analog, and again, to communicate to the outside world, you need to put an analog digital converter to communicate with the outside world. So depending on the kernel you want to speed up, on the function you're going to perform in your SIM core or your SIM accelerator, this you may need less or more complex blocks in your SIM. So, which meaning actually you may need to do more changes in the memory design or less changes. Okay, so we are talking about SIM-P, which means we are making major challenges in the periphery, right? So we may include a function here in the arrow or in the other periphery, right? But again, it's in the periphery. And we can have a basic SIM-P, meaning actually we don't touch the array at all. There is no change in the design of the array. We change only the periphery. We call it SIM-P basic. You can have also SIM-P hybrid, which means we may need some changes in the array as well. I will show you a couple of examples in the upcoming slides. Okay, but we get to SIM-A. So again, SIM-A means that I will produce my result in the array. It has also two SIM classes. So again, this is SIM-A and this is SIM-P. If I want to do an operation in SIM-A, I may have an operation applied on two operands, like here it's an OR. And so the output should be produced in the array. And the operands are also stored in the array. Everything is in the array. So we call it SIM-AR because in my case, I'm using these memristors or resistive-based memories. So this data, both operands are given in terms of R resistance. But I can have also a hybrid case, in which case one of the operand is, of course, the result should be present in the array, but one of the operand is within the array, and the second operand should come from the external port, right? So think about matching, for instance, or vector matrix multiplication, for instance. So you provide one operand through an external port, and in that case, we are talking about hybrid SIM-A. Systematically, the same thing for SIM-P. We may have SIM-PR, meaning I will capture the result in the periphery. Here is what I am doing the operation. But the operand I1 and I2 are both stored in the array. And in that case, we are talking about SIM-PR. Again, R stands for the fact that both operands are stored in the array. I can have also SIM-PH, and in that case, one operand will be coming through an external port, and one operand is already stored in the array, and they will capture my result still in the periphery because it's SIM-P. Again, if you are doing vector matrix multiplication or a matching, you can imagine one operand should go through external port to do your matching. And we are talking about SIM-PH. So this is kind of table that one of my students created. It's not actually complete yet about SIM-AR, SIM-AH, and SIM-P, etc. But I think recently most of work, at least my feeling, we still need to make this table complete. But I think recently most of the direction goes mainly towards SIM-P because it seems it's more promising than SIM-A, as I will also explain in the next slide. So now let's move to show you a design, an example of a design, how we do SIM-PR, Snyder logic, for instance.
Guess Said?
We lost Said, or
Yeah, we lost our keynote speaker. Okay. Let's see, hopefully. Said, do you hear us? You're muted. You need to unmute yourself. We lost you and your slides.
Oh, can you hear me now?
Yes.
yeah, now it's okay.
Sorry, I don't know what happened, guys. So
You have to share again your screen.
Yes.
I need to share again. Oh boy. Okay, something went wrong then. Share screen.
In the meanwhile, I can answer to Mohammed that yes, we are recording the session right now and we'll upload it on the MiM website. So you just need to go to the website in the past talks and then see the recorded videos of our past talks. And I think, Said, you need to go one slide back because, or maybe it was this slide, we lost you when you said, let's see SIM PR.
Okay.
Yeah.
So this was the last slide I discussed?
Yes, we heard you there, yeah.
Okay. Now I will show you a couple of examples about this design of SIM ER and SIM PR and SIM PH to give you a feeling about how does these designs look like, what is the good about them and what is bad about them, okay? So I will start with this Snyder logic. So it's actually SIM A, which means we are producing the region in the array and both operands are resistors. So this is the truth table. Let's take an example for 2 NANDs. And I will show this example for this case. P is 0, Q is 1, and the output should be 1. Typically, to do that, I need actually first to ensure that I am storing my data in the array, in the crossbar. So I'm using 2 control voltages, VW and VH. Give us certain threshold voltage for my memristor. So think about a memristor has a certain threshold voltage. If you're going to program it, you need a voltage below the threshold voltage, otherwise you will not be able to. So the first thing is to put the P to R on. This is my P, and 0 in that case is R on. So we need to put P in R on. So I need to provide the writing voltage to one of the nodes of the memristor and 0 to the other node to program it to R on. Fine. And keep in mind, you see I'm using here VH. Why this VH is selected in an appropriate way to ensure that the voltage across non-accessed device is below the threshold to ensure that they will never switch. For instance, here I am accessing this device, they apply VW, but because now it's 0 here and VH here, and VH is below the threshold. So this device and this device will not switch, will maintain the initial value they have. So this is the philosophy behind this condition. This condition is very important. Okay. So I will store my P and I will do the same thing for my Q, the same thing. And now I will do the computing. How should I do the computing? The first thing I need to do is to initialize an output device. That's very important. Means I will need a device where to put my output, and I need to access it, and I need to initialize it to R off. If it was one for whatever reason, it was already R on, I have to force it to R off because it's a condition for the good functionality of this approach. And then I will provide appropriate voltages for my VP, VQ, and VF. You see, VF now is put into VW in such way that the right result will be pushed in the output device. In that case, F will be R off according to these voltages. The key message here is actually you see that I am doing multiple accesses, right? So you see that is very nice. It's very suitable for the crossbar. We can get high density. It's a good news. But it requires multiple accesses. I need to initialize and process, initiate and process. And of course, the more access you will do, the bad it's for your endurance. And we know all these memristor devices, here, for instance, are suffering from still, as of today, probably in the future we'll have more materials, better endurance, but they suffer from the endurance issue. At least for those who are very familiar with memory designs are very, very critical. And if a team develops a memory, which is always squeezed all the way down to for the density purposes, they don't like to change anything. So it's there, it's fine, it's optimized. It takes months and ages to optimize it, leave it as it is. And here what we are saying, we have significant changes in the array in order to be able to perform this function while providing reliable, stable functionality of the Snyder logic or implied logic or stateful logic or whatever it is. Okay, so this is one of the, let's say, the challenges when it comes to SIM A. Let's now see how SIM PR works. Now, I'm capturing the region in the array, but in the periphery. I was draw the decoder, right? Select the appropriate location, get the current, put a reading voltage, and then a current will flow through this device. Depending on the state of M1, it's high ohmic or low ohmic, you will have a higher or lower current feeding this sensiplier. So this is the high current and this is low current, and I can put a reference in the sensiplier and distinguish between reading 0 and reading 1. This is just a memory, right? So I can change the memory, little bit change, in order to perform logic operations. So now instead of acting on a single cell, I will act on 2 cells simultaneously. So the current now that will feed your sensiplier, of course, you will need dedicated sensiplier. You need to change the sensiplier. The current that will feed this sensiplier depends on the state of M1 and M2. They can both be on, they can both be off, or one can be on and off, meaning 3 distributions of the current, as you can see. Okay, that's what I can get. And now if I would select my reference, I can develop a customized sensiplier and put the reference here. And I can assign this to 0 and this to 1. And what is this? This is nothing else than an OR operation. You see, by just minor changes in the periphery, I can perform bitwise OR operation in a constant time without moving the data at all, and in one shot, in one axis, not in multiple axis, in one axis. And also this is less demanding in terms of endurance because it's read driven. So this is very good for parallelism. I can do things in parallel. I can extend this, for instance, different words. Then I can enhance the performance. I can do one cycle per operation. It's good for energy efficiency. The endurance requirements. I am doing reduced communication. Of course, I don't move the data to the processing unit, so energy efficiency is good. It's read intensive, less requirements on endurance. But the bad thing, I need to ensure the data alignment. So when you're going to map your data in your memory, you should ensure that this bit and this bit are aligned in the same column, right? And of course, I need to make major changes. This should be modification and not modification. This is a typo here, okay? So I need to make a major modifications for the sensor amplifier and the address decoder, and minimum modifications for the array if needed. So in a similar way, I can do the AND operation, and I can even though create an XOR operation by providing dedicated 2 references. By providing dedicated sensiplier, I can do more operations. Okay, so in that case, I will need 3 references. Okay, and again here, less requirements on the endurance, 1 axis per operation. It's a very good, no major change in the array, but again, we need the modification of the sensiplier, address decoder, and data alignment. So let's move now to SIMPH, because this was SIMPR. SIMPH means actually 1 operand is stored in the array and 1 operand is feeding your memory, right? So let's talk about vector dot product. So here is the equation, and this is illustrates how we can do it. Assume 1 operand B is stored in your memory. Now that's the B, and 1 operand will be provided through the port of the memory. That's the A operand. So you can see here, assuming that 1 in that case is low ohmic. So if B is 1, it's low ohmic, right? So this is 1 if at least 2 bits, 2 midterms, in that one, A1 and B1 are both 1. Let's say if they are both 1, so this transistor will be selected, assuming I will pre-charge this bit line. And if this is on and this is pre-charged, and if this is low ohmic, this bit line will discharge. By discharging one of the bit lines, you can see that your output will be 1. So it's again in constant time, because all what I need, if this is 1, meaning low ohmic, and this is turned on, meaning 1, I create a discharge path, and then I can have a sensiplier, the dedicated sensiplier telling me it's 1 of the outputs. So I'm doing this equation, this dot product, in a constant time. It's a very good news. It's a constant time. I can even now extend this to vector matrix multiplication. I will just duplicate these columns. Again, you need, of course, the data alignment here. I can extend it to vector matrix multiplication. Vector matrix, it can be done in constant time. I can do the vector matrix in constant time. And matrix, I can do it in theta n. because my matrix has n vectors. So I will feed the first vector, the second vector, the third vector, and each time capture the result here. So you see, even though in time complexity, I am reducing. So it's a good news. You are reducing the time complexity, means you are reducing the energy and improving the performance. You don't move the data, so you are reducing also in terms of energy and in terms of latency execution time. So this is all good news. Again, the same thing here, data alignment, etc. What is placed and what's not. Another example for CMP operation is the multiply accumulate, which is an important operation for neural networks. Here, our SIM device consists of Memristor-based of conductances. I see G, I, J. You see them here. It's 1, 2, 3, etc. So performing multiply accumulate operation means actually applying a voltage here. Again, you have one operand here coming from the external port and one operand which is already in the stored in the memory. So this is the memory and this is the external port. So performing MAC operation means applying a voltage vector here, which has m elements in that case, to a matrix of conductors. And each column performs vector matrix multiplication by summing the current through all the conductors. So note also here that the MAC operation will be executed in constant time, which again contributes to the reduction in execution time. Obviously, the result will be analog and it needs to be converted or converted to a digital value. I take this from this paper, telling you how costly these ADCs. The red color gives you an analog digital converter, which we need actually to convert these analog values to a digital. And we have to communicate with the outside world through digital outputs, right? So this shows that, I don't know, shows that an area of ADCs offer 95% of the whole SIM device and 60% of the power is just consumed by ADC. These numbers, we did not verify them in our experiment, but it seems to be unlikely, it's too much. And this is also simulation based, but the message is clear actually. The message is that your analog digital converter is a bottleneck, it's a very important component if you're going to do neural networks. And we recently actually started also doing some research in these directions, and you have two new actually publications we produced in this field. Given the importance of this EDC, we thought let's first understand how this EDC works, right? So, and if you think about it, the EDC has three major phases, right? The first phase is sensing. Typically what happened is there, the EDC quantifies the input, the input, the analog input value, and after sensing, an immediate representation is given. And this intermediate representation could be a voltage, current, or time, according to all the state-of-the-art designs we analyzed. The second stage will be the conversion stage. So I'm just talking about the process of how EDC works actually, right? After the sensing, you create an intermediate value in terms of voltage, current, or time. Then the next stage is the conversion stage. And in this stage, these quantified values will be converted to digital samples. And these samples could be in terms of pulses or even though in digital bits, interim digital bits, right? That's what you call conversion stage. And after the conversion stage, you have to go through what you call decision stage. And in this decision stage, you have to convert the intermediate digital representations to the final output, which could be encoded in different formats, such as digital or digital combining multiple bits or other formats, depending actually on the application that should be fed by the output. Given these three ways of representing the intermediate stage and the analog and the three intermediate stage of digital, we defined kind of 6 EDC classes, 3 times 2. And we did kind of analyze the state of the art. We see here all the different state of the art. Very interesting result. We found some very interesting results. The number one is you see here, if your first stage, your sensing stage is, or intermediate representation is given in voltage, you typically end in high latency. You see, this is the latency, this is the power. So this is V, D. V means that the first stage is voltage, and the second stage is digital or interim. So you this VD, they consume typically a lot of area because the circuits are large areas, big areas. But in terms of power, they consume a lot of power, a lot of area, but they score very good in terms of latency, right? You see that because this is latency. And if you move to using the current instead of voltage, you see that the area is smaller. This is the current. This is the current. So area consumed by the ADCs is much smaller, right? And latency starts to grow a little bit, okay? So, and here the message is, depends on the application, depends on the requirements. You may try to explore some designs, some classes rather than the other classes. If you are mainly concerned with the energy, is different. For example, if you are mainly concerned with the energy, you would better take a look at the designs which are, less energy consuming. And energy, of course, is the power of latency. But if, let's say, your latency is a major concern and you need really to react very quickly, then you will be able to trade off more area and more power. So actually, these classifications give us a good insight to see which designs we have to explore depending on the application. But the key message here is that the ADC designing an appropriate ADC with appropriate accuracy, low energy, and high speed will remain still a major challenge. And I am sure in the future will be a lot of research. We'll see a lot of research in this direction, especially if we know that these Memristor devices, they have to suffer from a lot of non-idealities, like endurance issues, like drift issues, like the aging issues, like degradation, and this somehow should be compensated during the calculation for the accuracy. So we'll see a lot of research in this direction in the future as well. This is another nice idea that I took from our colleagues from IPM. So just by changing the configurations of your periphery, you see now this are the A's, this is vector matrix multiplication, this is the A's, and this is the base. And now we will change the configuration. My S will be here. I'm just changing the configuration of the periphery. Instead of doing this matrix multiplication, I'm doing now transposed vectors matrix multiplication by just doing the configuration of the periphery. And the key question is now, can reconfigurable periphery enable us to do more functionality, more algebra calculations? So, by just configuring the periphery, I can do this calculation or that one, or this vector multiplication or that one, and so on. So this is a very nice aspect to explore as well. And the key question, of course, is at what cost? Before moving up to the potential of the SIM, quickly something about we recently are doing department. We are actually comparing imply or Schneider and starting motion. Remember, this is SIM P and this is SIM A. By exploring that for different R on R off ratios for DRAMs and different voltages. You see that here, red means bad operation, it doesn't work, and the green means that the operation passed correctly. The key message is actually that simply operates at low R of R on ratio, no problem if there is which means if there is a degradation of R on R of ratio of the years of the time, simply will still survive. This is not the case for SIM P. And also the operation for SIM P are at the low voltages, which means low energy. For SIM, for imply or SIM A, typically you require high voltages. So in conclusion, SIM A will have the potential to operate at low energy and will be less sensitive to device deviation and non-idealities. And this is a key message from this study, which is not published yet. Okay, so now let's move to what can we do with this combination memory? What is the potential? To start with the design flow, right? Because SIM will be an accelerator, right? Will be application domain specific, right? And this is actually what we see these days in all these accelerators as well. So the first thing you need to analyze is the application domain and identify what kind of kernel I would like to accelerate, right? Is that vector matrix multiplication? Is that analog? Is that digital? And this will identify your architecture. is that same PR? Is that same PH? If I'm doing vector matrix multiplication, then it should be hybrid. If I'm doing database query, then it should be sim P, for instance, R, because both operands will be stored in the memory. So already at this level, you may have an idea about what kind of architecture you would like to have. And then we'll start with circuit design. You need the array, of course. You need to think about the technology of the memory itself. Should I use ReRAM? Should I use PCM? Should I use STT-MRAM? Should I use DRAM? SRAM? For instance, we know that STT-MRAM is mainly binary, high or low, but ReRAM and PCM can be used in an analog manner. So they will be very suitable for neuromorphic computing, for instance, as compared with STT-MRAM. The same thing applies for the structure. How can it build my crossbar? How can it build my memory? We have different flavors. Should they make passive? Should they be make 1T1R? Should they? So there are different flavors. And how can they organize the hierarchy as well? So there are also different flavors there. The same thing applies for the periphery. How can I deal with my analog mixed signal design? I need the drivers, of course, raw decoders, write drivers, etc. But I need also dedicated sense amplifier, or maybe I need dedicated analog digital converter. Just saw in the previous slide how critical they are. The same thing applies for my digital part, the control, the analog, the address decoders, and so on. And all of this tells you one thing: to really optimize your energy, to provide appropriate accelerator, you need really a holistic approach that goes through all these different levels. Now, let me show you an example to illustrate this design flow. Assume we're going to do this for a database query. Assume we have a certain number of stars in the space. The stars are called E, B, C, whatever, T, L, H, and each star has a certain distance from this, from a certain difference, and each star has a certain size, which could be large, small, medium, and this is the year of invention. It could be any feature, of course. And we would like to do the database query, find data satisfying far or large. So let's try to make use of computation-in-memory accelerator. The first thing to do is to map this data set in bitmap index. So now these are my features, far, etc. And each column now gives one star. Your data, your operand, right? Okay. So now, if I would like to go for this query, find data which satisfies far or large, it means actually just ORing the row far and the row large and get the output. And this is my output. Now I can say that the star A and C and D satisfy this condition. So this is kind of my application and the requirement of the application. So if I would like to know to create a SIM accelerator, what I can do? What are the requirements? I need to do this bitwise OR. Fine. That's the kernel I would like to accelerate for this specific case. Fine. What kind of architecture can I use? I can use SIM-PR. Why R? Because both operands are stored in the database. What I can do, circuit design, I can use scouting logic to perform my operation. So this is to illustrate how the design approach should systematically work. Now, we did this work actually. Yeah, we did this, and by the way, for each slide you can find a reference where you can go back to learn more. So we did this based on simulation, analytical simulation. First simulation, and then I will show the demo. So we used, let's say, 40-bit data with for 4 CPUs. Each CPU had 32 kilo L1 cache, a lot of the details, etc. And then we tried to compare multi-core platform, 4 cores, with a SIM accelerator. We were changing the miss rates of our CPUs, L1 cache and L2 cache, and we were changing the size of the problem from 32 gigabyte to, what is it? No, we're changing the part of the problem we can speed up. 30% we can speed up, 60%, 90%. Let's say the size of the problem is 32 gigabyte, but only 30%, we're targeting only 30% of that problem, right? So what you see, this is the normalized delay. You see clearly the size of the part you are accelerating, 30%, 60%, 90%. The larger the size, the better the speed. This is the normalized delay. And the red colors here gives you what is needed for multi-core platform, 4-core platform, as compared with the baseline, which is our SIM, the green line, the green lane. Clearly, you can see that we can speed up the delay up to 30% X. If you take a look at the energy, I think this is the energy, yes, and energy is normalized to SIM. You can clearly, in energy, we always score better. because of course we don't do data movement. The device is non-volatile, okay? So, and very important, the larger the size of the problem, the better energy assignment. And this goes up to 100x improvement as compared with a 4-core platform. Let's now go see, this told us actually, yes, there is a huge potential. Let's see in the silicon if this is real. So together with our partners at IBM, we are all involved in a European project together. So our colleagues at IBM, they manufactured crossbars, PCM crossbars, 1R crossbars. So we did a lot of characterization to extract information from maybe they did at IBM, so mainly to extract information such that we can build calibrated simulation models. And we created 41 times 303 crossbar circuit. Again, these are calibrated spice models, which are based on real characterization data. And in addition to that, we created some smart designs in the periphery, like what you call cascade logic, because this cascade logic, this is just as an illustration, allows you to do 2 logic operations in one clock, in one shot, in one clock cycle, right? So we put some delays in. So, and we use this in, we did this implementation in 65 nanometer technology, and we assumed we have a database query which has 41 times 303 crossbars. We assumed that this was done for patient and healthcare application, etc. So the idea is now we wanted to do a real simulation or measurement, if you want to call it, for a 11-step query, like I showed in the previous slide, database query. So 11-step query was done in 30 nanoseconds using this information. Huh? So meaning almost 100 gigaops throughput. And the total energy for this specific case was 20 picojoule. The power was almost 516 microwatt. This means actually an efficiency of 166 teraops per watt. In other words, we are talking about 6 femtojoule per operation. This is very remarkable. The question is now, what does it mean? Let's place this in perspective, okay? So one of my students created actually this, one of my postdocs created this nice picture because it helps us to better place the found energy efficiency in our experiment and to show, this actually shows the most recent computing engine, in particular developed for targeting AI. You see, for example, Spinnaker, you see TrueNorth, you see Loihi of Intel, you see TPU, you see all of them here, right? And wanted to place the potential of SIM. Oh, what is it? Hold a second. Okay, so I wanted to place the potential of SIM. We are talking about 6 femtojoule per operation. So we are talking about this kind of order of magnitude energy efficiency, close to femtojoules per operation. And so SIM probably, where is SIM? Hello? Oops, okay, this one's very quickly. Okay, so SIM will bring us to this order of magnitude. So femtojoule per operation. So we are talking about 10x, 100x, maybe even 1000x better than the state of the art. And if this will become, I don't know what's going on.
Said, I don't know also how long you have or how many more slides you have, but
I'm going to the conclusions. So
yes, thanks.
Yeah. But my computer is stuck. Just oh boy. Quite strange. It's asking me to restart the program. I will restart the program. I don't know what's going on.
Yeah, sure. This today was not very lucky.
Okay, I will
Your computer.
do this. I will go immediately to the slide. Okay. 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 Can you see my screen or not yet?
Not yet.
Okay. Share screen. Share. And now?
Now we are seeing it, yes.
So the idea, if this becomes a reality, if this numbers I showed in the previous becomes a reality, then we are really talking about being able to deploy SIM at the edge, where the requirements in terms of energy efficiency are extremely severe. Okay, let me now move to the major challenges. So as you can imagine, there are challenges from different levels, from tools to applications. We need to bridge, let's say you have an application, you need somehow to develop mapping tools to be able to map your application on the crossbar, on the SIM. We already talked about, for instance, data alignment. We need also how to deal with the microarchitecture and also how to deal with intra and intercommunication. We need to scale this. We cannot create a single huge crossbar. We need to have multiple crossbars, how to deal with the hierarchy, how to deal with the intercommunication. We need also to deal with circuit design. I already mentioned the importance of EDCs are very important, how to deal with that. So how we can provide appropriate designs that can enable the offer energy efficiency. Also technology, the variability. This is a real picture that we got from in collaboration with our partners in France. You see how this R on, R off, sometimes it's low. So this R on, R off variability, how to deal with it, what could be the impact on your calculation, the accuracy of your calculation? Do you need to integrate some intelligence, some self-healing approaches in microarchitectures to deal with that? This should be the trend in the future and so on. Another aspect which is very important is testing. We have been doing a lot of work together with our industrial partner, which is making real use of real silicon measurements. We figured out that today test solutions will fail to test appropriately the SIM devices, especially those using imaging devices like Memristors and ReRAM and STM. So we validated this really using the measurements. And here is an example actually that this is based on ST microelectronics chips. And we have actually a paper on about it. It will be presented at European Test Symposium in a couple of days, I think next week. So we figured out something quite remarkable, very strange. You see here, so you are not your device intermittently, so which means from time to time, is switching to. It's supposed to be in a set mode, but it's switching to reset mode. And this is intermittent. You cannot. It's not permanent there. So these are kind of phenomena which I'm calling them. We are expecting some known unknowns. So we have to understand them and develop appropriate solutions. I will skip this testing part and I will go to the conclusion immediately. So in conclusion, imaging applications requires new chips. If you're gonna deploy AI at the edge, we need to rethink about microarchitecture, design, security, communication, and we need to be able to realize order of things to joule per operations. Yeah. Key enablers are new architectures, new technologies, SIM, artificial neural networks, view-inspired computing, automata processors using imaging devices could help. And I talked mainly about using emerging non-volatile devices, but we can also make use of 3D processing, monolithic or non-monolithic. We can also think about photonics for communication. These are all technologies that can be explored. And we have seen that the potential is extremely huge, not only because of there is no data communication, but also we can reduce the complexity of the functions that we have to perform. And of course, there are many challenges ranging from technology up to architecture, testing, reliability, and very important, being able to demonstrate the potential for a full application evaluation. Today, what you see most of the time, we are publishing, the community is publishing mainly about isolated kernels, like I did also when I showed the demo. But the long term, we really need to develop a full application and evaluate the full application with all stack, including the software stack and the whole communication and so on. And this will give us a better feeling about the potential. I will end with this nice picture that I actually took from IBM website recently. They are showing actually the trend. So the blue ones are where we are standing today in terms of energy efficiency, gigaops per watt. The blue are commercial, making use of CMOS. People predict that we'll still make use of the CMOS in the future, in the near future, while making digital AI cores, but maybe thinking about more approximate computing, because some applications, they don't need accurate calculation anyway. For the long run, we're gonna move to analog AI cores. And this is exactly using memristors for in-memory computing. And for the long run, even they will need to think about how we can optimize these memristors and PCM using new optimized materials. So which means there will be a huge research in materials in order to help the device community in order to help the quality of the device and therefore enable or enhance a better analog AI course. With this, I would like to thank you and end my presentation. I would like to thank some of my partners like WTH in Germany, IBM, ETH Zurich in Switzerland, IMEC in Belgium, Eindhoven, TU Eindhoven in the Netherlands. Thank you very much. And I will be happy to take some questions.
Thank you, Said, for the very nice presentation. I'll stop the recording and we can start the discussions.